Sorry, if you want, yeah, as I said, that Alessandro provides a good introduction for what I'm going to be talking about here, but using a slightly different approach. So in this case, I'm going to be sort of describing the results of a trial to use sort of machine learning to correct spectral wave forecasts at a specific site rather than in an ocean basin. So this is work with Kevin Vinson, who's a data scientist here at UWA, and the team at the Bureau of Meteorology. So obviously, don't need to tell anyone or convince anyone here, but obviously wave forecasting is critical for industries and marine safety and all of that. And as Alessandro illustrated, that while we have these very computationally efficient spectral wave models, they are prone to biases and errors, which are related to parameterizations of the physics, like the wind growth, but also just boundary conditions and practical considerations of spectral resolution and grid size and bathymetry, for example, particularly in shallow water. And I think this figure on the bottom illustrates the issue well, particularly as it relates to industry in Western Australia, Northwest Australia, particularly is the issues around arrival times of new swells, and these are often swells generated in the Southern Ocean. You're very likely to get swell arriving 12 or more hours late, or sometimes 12 or more hours early, which can be quite an issue for planning a number of operations like berthing, for example. So despite a lot of the efforts in improving the physical parameterizations and spectral models, the improvements have really sort of slowed. And so that's why I think you've seen a lot of focus on using data assimilation and the like. But also, I'm going to sort of try to take a slightly different approach and see if we can use all of the new developments in machine learning to correct the forecast or identify the forecast. So what we're going to do is we're going to use machine learning here as a trial to see if we can identify and correct numerical wave forecast from a WaveWatch 3 model in this case for a specific forecast location, which is at Barrow Island in the northwest shelf of Australia. So Barrow Island is a bit of an interesting site. It has quite a large port facility there, and it has the swell. I mean, the spectrum is often bimodal, with you get swell from the Southern Ocean that's actually has to refract around both sides of the island, and that's the refraction around island is sort of a known issue in spectral wave models. But also because it sits a couple hundred Ks offshore, depending on where you measure, you actually have a bit of a fetch for local wind. And most of what I'll be talking about is trying to improve the forecast for that those locally generated seas, which occur when you get very strong easterly winds, particularly in the winter months. Because of the way that the facility was built, it turns out that the way the bursts are oriented, that half the wavelength of a 6-second wave turns out to be about the beam of some of these ships. In the way that the bursts are oriented, that's often beamed to the sea. So our objective here is to not sort of take the complete black box approach, which is becoming somewhat common. We're not totally using the machine learning model to replace the physics-based spectral wave model. We're basically just trying to improve the existing WaveWatch 3 model and just see if we can identify and fix errors around the edges. So what we've done is we've taken the existing Bureau WaveWatch 3 model. So that's an unstructured model that has high resolution up to 250 meters around the island and along the coast. And that's nested in their global all-wave model and is coupled to the Access Generation 3 atmospheric model. So that's sort of the latest atmospheric model. So this is our starting point, this relatively high resolution WaveWatch 3 unstructured wave model. So what we've done is to see if we can improve or identify errors in the forecast and then ultimately result in an improved forecast. We've trained 4 different independent machine learning models using 2.5 years of archived 7-day wave forecasts at the forecast point. So these are the spectral forecasts at that point at the end of the jetty, and those are issued every 12 hours for 7 days at hourly intervals. There's a wave rider buoy located at that exact same location that we have data for. We're taking the modeled wind conditions, and then we're also including tidal water level predictions because the tide range is on the order of about 4 meters or so. And the water is relatively shallow, so that's going to have an impact on the propagation. And as typical practice, we withheld 20% of the training data set for calibration and validation system. And a key difference of what we're trying to do, and this again sort of follows on a little bit from what Alessandro was saying, is rather than try and just predict the bulk parameters, so the significant wave height, period, and direction, we're actually trying to do this all in spectral space. And initially, what I'm going to show is the 1D spectra, but we're planning and we're working on extending that to the 2D spectrum. And that's really important because it provides a much richer data set that we can use to look at the sea and swell partitioning, which can be used to try and understand, for example, vessel dynamics and other things like that. So I'll give a bit of an overview of how this actually works before getting into a bit more detail and showing the evaluation. But essentially, we have the Bureau 7-day forecast of the spectra and the wind conditions that feed into these 4 different deep neural networks. And we're also including the previous 12 hours of forecasted so the models can actually see essentially what the weather pattern has been over the last 12 hours. We're including the tidal water level predictions, and that's just based on a simple harmonic analysis I've done of the tides. And then we're including the buoy data for the training. And not unlike what you do with a numerical model, because we have these 4 different machine learning models, we're actually combining those into an ensemble. And the ensemble itself is actually a different machine learning model, which I'll talk about in a second. And then from that, once we have that revised spectra, we can calculate all of the sort of standard parameters that you would for a forecast. And just something to point out is while we have the Bureau is doing 7-day forecasts, in our case, we're cutting it off at 5 days. And that's because we did some initial tests, including the full 7 days. And the machine learning models were struggling a little bit because the variability in each 12-hour forecast, so each time that the forecast is updated, in that day 6 and 7 of the forecast can be very variable. And the models were struggling with that, so we cut it off at 5 days. So just to sort of illustrate what this would actually look like. So on the top, we have the one-dimensional spectra with time on the x-axis and the frequency on the y-axis. So essentially, this is the Bureau spectra. This is our input. We feed that into our machine learning models, and we get essentially revised one-dimensional spectral forecast. And then I'm showing here on the bottom what the observations ultimately were for that time period. So I'm not going to get into the details of the machine learning a whole lot, particularly because Kevin Vinson, my co-author, is really the expert in this area. But the 4 different models that were used were a GRU, so a gated recurrent unit, a one-dimensional convolutional neural network, a 1D ResNet, and then what's called the dense neural network. And these are machine learning models that are pretty common in applications like speech recognition and the like. And then one of the things that we've done, which is a bit different, is that we've taken these 4 models, and as I mentioned, we've combined them into an ensemble. And rather than being sort of a normal kind of ensemble that you would do with a numerical model, the ensemble in itself is a sort of a 5th machine learning model, and that actually basically learns how to independently weight the different four models, the input four models, based on their performance for, say, different times of the year, right? So during, say, January, one of the models may work better than the other versus in June, a different model may work better, and that's accounted for in this machine learning model that is the ensemble procedure. So because at Barrow Island, particularly, as I mentioned, we have this really bimodal spectral often, and these really strong easterly winds occur mostly in the winter months when there's a high pressure that moves north over Australia. Rather than have one sort of model that accounts for all conditions of the year, what we decided to do was make a different sort of machine learning models for each month of the year. And that's really to take into account that we don't really want the conditions from January, which are very much different, being incorporated into the forecast system for June, which has a much different wave climate. And what we've done is we've essentially taken from the first of the month, the machine learning model for that month includes that from that day plus or minus 1.5 months. So the model for June, for example, would be from mid-April through mid-July. And this all runs relatively efficiently. The training takes a fair bit of time on a GPU, but once the models are made, they are essentially run within about 10 minutes immediately after the Bureau forecast was issued. And that's just on one node on the NCI. So what we did is we set this up in a sort of quasi-operational system to run on the NCI alongside the Bureau's operational forecasts for July through October of 2021. So this is a time period that's never been seen by the model because the model was trained up using data up to May 2020. And that resulted in 194 5-day forecasts. And so to evaluate the model and performance improvement, if any, what I'm doing is essentially calculating the root mean square error, both the Bureau and the machine learning model against the spectral observations recorded by the wave rider buoy, which is all sitting more or less at that forecast point at the end of the jetty. And another thing just to mention is that we're really only evaluating the conditions when the significant wave height as observed by the buoy was greater than 15 centimeters, because that's the minimum wave height that's forecasted in the Bureau model. All right, so just to get to the what this actually resulted in. So as compared to the Bureau forecasts, that in the ensemble machine learning approach, it reduced the average forecast errors for 11% for wave height. That was for conditions where it was greater than 15 centimeters. But if we look at larger conditions, say when conditions were larger than 25 centimeters, we see that reduction in error actually improves for the larger cases. And we reduced the average forecast errors by 41% for peak wave period. So while the peak period may not be the best that you would calculate, particularly with this bimodal sea state, we stuck with that because that's the standard forecast parameter provided by the Bureau. And now we can slice this up day by day to see how these errors varied as each day of the forecast. So the left is for the wave height, and so you can see for day 1 and 2 of the forecast, we're actually basically about the same as the Bureau model. But then we're starting to reduce the errors more and more as we get into days 3, 4, and 5 of the forecast for wave height, whereas the improvement's pretty uniformly for the peak period across that 5-day forecast interval. All right, and just as I mentioned, we issued 194 forecasts between that time period between July and October, and this essentially plots what the average root mean square error is for wave height for each of the 5-day forecasts. And basically, we were able to make improvements to the forecast, so reduction in the forecast errors for 2/3 of those 194 forecasts between July and October. And so we were pretty happy with this as a trial, particularly given the limited training data set. So again, only 2.5 years of data went into making these models, which is pretty short in the sort of machine learning space. So rather than just focus on the bar plots and the like, I thought it would be helpful to show a couple examples of what these forecast time series look like. And so again, rather than focusing so much on how the spectral looks like, I'm focusing on the parameters that are delivered really as part of the forecast. So in these time series plots, the black line is the wave height or the peak period as forecasted by the Bureau. The blue is what the machine learning is predicting, and then the red is what was actually ultimately recorded by the waveguide. And so in these plots, you can see basically these diurnal peaks, and these are associated with those strong easterly winds that tend to spin up late in the evening as the essentially the land breeze develops when the land becomes much cooler than the water, which is usually in the high 20s. So at about 8 or 10 o'clock every night, you get these easterly winds spinning up. They generate waves over that 100 or so kilometer fetch, and then sort of those winds drop off, say at 10 o'clock in the morning or so as the land heats up during the day. So each of these diurnal peaks, the model in this instance, I'm not going to lie, they don't always look this good, but the machine learning forecast is resolving both the amplitude and the timing of those peaks better than the Bureau model. Just another example here. In this case, again, resolving the amplitude and the timing. But one thing I'd like to point out, and I'll show this in a little bit more in one of the other slides, is basically the machine learning models have do pretty well predicting the swell, and that's because they've more or less learned that the Bureau almost always over-predicts the swell wave height. Partly because of just the way that the spectral wave model resolves refraction around the islands, but the machine learning model struggles getting the shift in the peak period when the swell arrives, which you can kind of see there towards the 10th of September on the bottom right. And then just to show an example of an instance where the machine learning model actually did worse than the Bureau forecast, both under predicting the amplitude and the timing in this case. But on average, over that period, the forecasts were improved in majority of the cases. So by predicting the 1D spectra, we can then slice this up and look at how the model does for C and swell. And so for the C periods, if that's periods, wave periods less than 10 seconds, we reduced errors by 15% for wave height and 8% for the swell wave height. And
Jeff, sorry, you've gone a bit over time already. So can you try to wrap up?
Oh yeah, sorry. Yep. Okay,
Go
ahead. And just didn't do nearly as well for the peak period. All right, so this is the last slide. But basically, I think from this trial, we've shown that the model actually works pretty good from a limited training data set. And just to say the next steps that we're working on this is extending this to the 2D spectrum for obvious reasons, incorporating real-time observations to do interim forecast and incorporate continuous learning. Thank you. That's it.
Okay. Thank you, Jeff. Very interesting talk. We have a question from Raphael.